Nothing beats another video, and this time we are going to focus on the concept of horizontal asymptotes, and we'll also look at some examples as well. So let's take a look. All right, we're just going to start by considering the function, the elementary arctangent function. F of x here is the arctangent of x, and of course, to remind ourselves of what this function's graph looks like, got the graph given on the screen right here, and there it is. What we want to point out in relationship to our idea about horizontal asymptotes is that there's these two horizontal lines that we can see drawn on the graph here, one of them being y is equal to pi over 2, and the other one being y is equal to negative pi over 2. And in fact, for the arctangent function, both of these horizontal lines are indeed horizontal asymptotes of the arctangent function. Now, why is that? It is because of the behavior of the arctangent function as x goes to infinity or negative infinity. Notice on the right in quadrant 1, we could write that the limit as x goes to infinity of the arctangent function is equal to pi over 2. That's because as x gets very, very large in the positive direction, this arctangent function is approaching that horizontal line, y is equal to pi over 2. And similarly, down there in the bottom left, we could write a statement that limit as x goes to negative infinity of the arctangent function is equal to negative pi over 2. Again, that's because as x is going to negative infinity, the function is approaching this horizontal line, y is equal to negative pi over 2. Now, these are both of these horizontal lines, that is, they're both examples of horizontal asymptotes. And so I just wanted to start the video by showing a specific example of, like, here's a graph that has two horizontal asymptotes. And why are we having horizontal asymptotes here? It is because of the end behavior of the function. And so we can define a horizontal asymptote using this idea, and that is as x gets very, very large in the positive or negative directions, if my function is approaching a particular output value, in this case pi over 2 and negative pi over 2, then those horizontal lines, y equal to those numbers, are horizontal asymptotes of the function. So here is our definition. In general, we say that a horizontal line, y is equal to a being some real number here, horizontal line is called a horizontal asymptote of a function, say y is equal to f of x, if either of the following are true. So could be one or the other or both. And that is, like we saw in the previous example, if you have that the limit of the function, say as x goes to infinity of the function, is equal to that particular number a. So you can see in the graph given here on the screen that in this case, as x is going to infinity, the function is approaching the output value y is equal to a, and hence the limit as x goes to infinity of f of x is equal to a, and thus y equal to a, that horizontal line, it is a line, so we have to write it as an equation, that is a horizontal asymptote for the function f of x. So that could happen, or you could have the other direction happening, and that is if x now goes to negative infinity and my function approaches some unique real number a, as we can see in the diagram on the screen, that's happening, and thus y is equal to a is a horizontal asymptote for the function f of x. So really horizontal asymptotes are just horizontal lines for which a function is approaching that output number if x gets very, very large in the positive direction or very large in magnitude in the negative direction. Long-run behavior, function approaches some particular output value, then y equal to that output value is a horizontal asymptote for the function. So that's how we define it. And you can see how it relates to the previous video on long-run behavior. And so what we're going to do now is we're going to look at a few examples, just figuring out what long-run behavior is for each of the following functions. And if there is a horizontal asymptote, then we'll state it. Let's start with this function right here. F of x is this rational function, 2x to the fourth minus 6x squared plus 13 divided by 5x to the sixth plus 4x cubed plus x minus 4. Now that's a rational function. And perhaps you remember some ideas back when you studied rational functions. Of course, they are ratios of polynomials, and each polynomial in the numerator and denominator have a particular degree associated with them. In this case, the degree in the numerator here is 4, and the degree in the denominator is 6. So in this particular case, remember that if the degree in the denominator for a rational function is larger than the degree in the numerator, then this function is going to approach 0 as x goes to infinity and as x goes to negative infinity. So up here we can write limit as x goes to infinity of this function f of x, without having to rewrite the whole rule here, is going to be equal to 0. And in fact, limit as x goes to negative infinity of the function f of x is also 0. And for that reason, it follows that the line y is equal to 0 here, this is a horizontal asymptote for the function f of x. So we can use that information about rational functions to figure out its long-run behavior, but I will show in the next example a more algebraic way to do this if you wanted to. And just to confirm it through the graph, here is the graph of the function we were just looking at, y is f of x. And as you can see, as x goes to infinity and as x goes to negative infinity, the function is indeed approaching the output value of y is equal to 0. And hence, y is equal to 0 is a horizontal asymptote for this function. Let's take a look at another example. Another rational function. In this case, let's call it g of x. We will look at a couple of examples of functions which are not rational here in a moment. But just sticking with the rational function g of x here, we can notice that we have a cubic polynomial in the numerator and a cubic polynomial in the denominator. And so when the degrees are equal in the numerator and denominator of a rational function, then we recall that the function will approach the ratio of the leading coefficients of the polynomials in the numerator and denominator. And thus, we can write that the limit as x goes to infinity of g of x is going to be equal to, in this case, ratio of the leading coefficients is a -2 divided by a 1, so it will approach -2, and in fact, it will happen in the opposite direction as well. As x goes to negative infinity, the function g of x approaches -2. Now, of course, we're using that knowledge from, say, pre-calculus or whatever you studied it. However, is there an algebraic method for figuring this out for rational functions? Indeed, there is. And so I just want to, give caution here. What I'm about to show is only relevant for when you're looking at the long-run behavior of a rational function in particular, but there are kind of similar methods in some cases for other types of functions, which we'll look at in this video as well. And that is what you do if you want to do it algebraically, is you look at the highest exponent on the variables out of all the different terms in the rational function. In this case, the highest exponent happens to be in two different locations, and that is a 3. So what we do is we multiply by 1 over x to that highest power in the numerator and denominator. Oops, I wrote a 4. Should be a 3. Like so. Again, it's the highest degree out of all the terms that we see in a rational function. We can apply this method if we are talking about x going to infinity or negative infinity. Because, of course, if I divide 1 by x cubed, I got to worry about it being undefined. Since x is 0, we'll make it undefined, but we don't care about that since we're looking at the long-run behavior. Now, when I do such a thing, I multiply all the terms in the numerator and denominator by that 1 over x cubed. So what it's going to do is going to transform it into an alternate form, and that is, all right, just think negative 2x cubed times 1 over x cubed. Well, the x cubes cancel. You get a negative 2 for the first term on top. 3x squared times 1 over x cubed leaves me with a plus a 3 over x. And then we're going to have another plus here. 4x times 1 over x cubed is a 4 over x squared. And then minus a 1 over x cubed. In the denominator, x cubed times 1 over x cubed is just a 1. And then minus a 2x squared times 1 over x cubed is a minus 2 over x. Plus a 5x times 1 over x cubed is a plus a 5 over x squared. And then plus a 4 over x cubed, right? So this, again, is true for x not equal to 0. And then I could take the limit. So notice now, as x goes to really infinity or negative infinity, right? What's going to happen to this new form? Well, notice that any of those terms that has an x power in the denominator, they're all going to go to 0, right? So this term's going to go to 0, that term's going to go to 0, that term's going to go to 0, that's going to go to 0, 0, and going to 0. That's because as x gets very, very large in magnitude, you're dividing a constant by a gigantically large number. And thus, what are you left with? That ratio of the leading coefficients, just like we concluded a moment ago. So as we can see, as x goes to infinity or negative infinity, the function g of x goes to negative 2 over 1, which is negative 2. But that's already what we concluded up here. But I just wanted to show that alternative kind of algebraic type method for looking at long-run behavior of rational functions. So it can be done. And the reason I show that in this example is because we're going to kind of do something similar in another example here in a moment. Now, just to see the graph, to see it happen, here is the graph of the function we're just looking at. And indeed, notice that as x goes to negative infinity or as x goes to infinity, this function is approaching this line, y is equal to negative 2, this output value, and hence this y is equal to negative 2 is a horizontal asymptote of the function g of x. Right? It's that horizontal line. Now, sometimes people ask, or say, I guess, hey, the function is crossing the horizontal asymptote at this location. That's not allowed. Well, that's no big deal, right? Functions can cross their horizontal asymptotes, just to put that out there. All we care about to define a horizontal asymptote is if in the long run, as x goes to infinity or negative infinity, the function is approaching that output value. And indeed it is here. We don't care whether or not it crosses this line. All we care about is long-run behavior. So nothing wrong with that. All right, now those two are rational functions we just looked at. Let's look at a couple of examples in which we don't have rational functions, but they kind of have similar types of methodologies, if you will, in finding what their long-run behaviors are. So in the next example, here is another function. Let's call it h of x. And this time we have in the numerator 10x cubed minus 3x squared plus 8. But in the denominator now, we have the square root of 25x to the 6 plus x to the 4th plus 2, all inside the root. So this is not a rational function because of the root in the denominator, but it kind of behaves like a rational function in some ways. And so now we can't just use those facts from, say, pre-calculus about rational functions and their long-run behavior. We have to do something else. We have to kind of get to a new form of this function for which we can see its long-run behavior, kind of similar to how we looked at the last one. Now, for this one, if you kind of just look at the denominator here inside the root, obviously inside the root is a polynomial function of degree 6. And so we should expect that as x gets very, very large in magnitude, that polynomial inside the root will approach, the according infinity or negative infinity direction based on the leading coefficient of 25 and, of course, the degree of that polynomial, 6. Now, it's inside a root, right? Square roots are strictly increasing functions, so we know that the behavior here is as I just described. But algebraically, how are we going to get around this? Well, because this term right here, 25x to the 6 for that polynomial, is the term that tells us what the long-run behavior of that polynomial is, then those other terms, x to the 4th and 2, they don't matter in the long run, right? The 25x to the 6 dominates. And so we kind of just think for a moment, well, in the long run, those two other terms don't really matter. And so if I just kind of disregard those in the long run, we can kind of think of, well, if I were to take the root of 25x to the 6, then we would have a 5x cubed, right? Depending on the value of x, if it's positive or negative here. And so for that reason, you think, oh, it's kind of like a rational function. I have a cubic polynomial up here. And if somehow I were able to take the root of that polynomial inside the radical, I would have a cubic as well. And thus, what I want to do here is multiply by a 1 over x cubed for that reason. Now, notice that 1 over x cubed, just off on the side here, 1 over x cubed is equal to 1 divided by the root of x to the 6th if x is positive. So we have to recall when I take the root of a square, right? If I take the root of something squared, that's the magnitude of that thing. Say the expression is a. And so we have to be careful here because this root of x to the 6th is going to change depending on what the sign is of x. And so in this case, we're kind of just starting with the case as x goes to positive infinity for that reason, right? Because if x is positive, then the root of x to the 6th is just x cubed. So when I do that, in the numerator, right, again, for positive values of x only, I get a 10 minus a 3 over x plus an 8 over x cubed. Now in the denominator, again, I'm multiplying the root by 1 over x cubed, but again, that's the same as multiplying by 1 over the root of x to the 6th, because x is positive. So I can absorb the root inside the other root, right? A root times a root is the product of the root is the root of the product. And so what I'm going to get is root 25 plus a 1 over x squared plus a 2 over x to the 6th. Again, that root is getting absorbed inside the other root. So when I multiply everything inside here by 1 over x to the 6th, then I get the result that we see right here. So now, as we can see, that as x goes to infinity, the numerator goes to 10, the denominator goes to root 25, right? So this is as x goes to positive infinity, which of course is 10 over 5, which is 2. And hence, we should conclude that the limit as x goes to infinity of h of x is equal to 2. Long-run behavior, at least in the positive direction. So, y is equal to 2 is a horizontal asymptote here for this function. Now, what about as x goes to negative infinity? Well, as x goes to negative infinity, we could do the exact same process that we just did above. However, we must recall, again, over here, the thing I'm circling, that the square root of a square is the magnitude of that expression. So in this case, we note that if x is negative, then the square root of x to the 6 is actually going to be negative x cubed. And that's because a negative times a negative x quantity cubed is going to be a positive. And thus, everything will be exactly the same as we wrote above. However, in the denominator now, we're going to have a negative root of 25. And thus, as x goes to negative infinity, my function h of x is going to approach 10 over negative root 25, which is 10, of course, divided by negative 5, which in this case is a negative 2. And thus, we can write the limit as x goes to negative infinity of the function h of x is negative 2. The long-run behavior in both directions. And so, just to see the graph, as we just concluded, here you go. Here's the graph of the function h of x that we were just investigating. As we can see, as x goes to infinity, the function approaches positive 2, and as x goes to negative infinity, the function approaches negative 2. And for these reasons, both of these horizontal lines here, y is equal to 2 and y is equal to negative 2, both of these are horizontal asymptotes of the function h of x. So a function could have one horizontal asymptote or two, or of course there's many functions that don't have any horizontal asymptotes. But here's another example of one that has two different horizontal asymptotes. And I got one last example to show you before we end this video, and that's to look at the long-run behavior of this function right here, k of x, which is 2e to the negative x plus e to the x in the numerator, divided by 3e to the negative 2x plus e to the x in the denominator. Now this one, definitely not a rational function, right? Because we have ratios of exponential functions that are being combined. So you think, well, what's going to happen here? Can we do something similar like we did in the previous couple of examples? Let's start by investigating what happens as x goes to positive infinity. All right, so let's first start with limit as x goes to positive infinity of this function, 2e to the negative x plus e to the x in the numerator divided by 3e to the negative 2x plus e to the x in the denominator. Now, we remember our behavior of exponential functions as well. When you have an exponential function of growth, in this case we see an e to the x and an e to the x on top and bottom, then those functions are going to go to positive infinity since they have a positive coefficient in front. And then for exponential decay, right, the e to the negative x and e to the negative 2x terms, those are going to go to 0. So we can see right away that as x gets very large in the positive direction, that term right up there is going to go to 0. This term right down there is going to go to 0. And then we're left with e to the x over e to the x. So that's going to go to infinity over infinity. Now, sorry to tell you, infinity over infinity is not necessarily equal to 1. Instead, that's another example of an indeterminate form. similar to 0 over 0 like we looked at in previous videos on limits. So when you have an indeterminate form, which is an infinite quantity over another infinite quantity, we have to do other things. We have to somehow do some type of algebraic manipulations on the function while taking the limit to see what the actual limit is. So to do this here, what we'll do is, again, we'll rewrite the limit in its original form. Limit as x goes to infinity of 2e to the negative x plus e to the x divided by 3e to the negative 2x plus e to the x. So the reason why this function is approaching infinity over infinity, an indeterminate form in this case, is because of the e to the x terms on the numerator and denominator. So we think, could we get rid of those e to the x terms by multiplying this function by something that is, I guess, clever, if you will? And sure we can. To get rid of those e to the x's, we can multiply by e to the negative x on both the numerator and denominator, noting that e to the negative x is never 0, so we don't have to worry about anything there, even though x is going to positive infinity. When I do this, I get the following equivalent limit as x goes to infinity. Just multiply everything by e to the negative x. So 2e to the negative x times e to the negative x is going to give me a 2e to the negative 2x, remembering our rules of exponents. And then e to the x times e to the negative x is just a 1. So we're left with that on top. In the denominator, 3e to the negative 2x times e to the negative x is 3e to the negative 3x now. And then we'll also be left with a plus 1 here as the last term, e to the x times e to the negative x. So it's kind of a similar technique, right? In the other examples, when we had powers of x, we were multiplying numerator and denominator by 1 divided by x to some particular power. When we have this kind of situation with combinations of exponentials, we can multiply by the base of the exponential, in this case e, to some different power of x that helps us manipulate the function. So now what we can see is, okay, it's in this good form now, because this is still decay as x goes to infinity. That goes to 0. That also goes to 0, and hence we're left with 1 over 1. Thus this limit is equal to 1. So we can write limit as x goes to positive infinity of k of x is equal to 1. It's long-run behavior in the positive x direction. And then finally, we'll look at as x goes to negative infinity. So let's take a look. Limit as x goes to negative infinity of this function, 2e to the negative x plus e to the x over 3e to the negative 2x plus e to the x. What happens? Well, now we're going in the negative x direction. And so in this situation, e to the x and e to the x are both going to go to 0. And we're left with that ratio 2e to the negative x divided by 3e to the negative 2x. But those are both decay functions, so as x goes to negative infinity, again, both of those are going to go to infinity. And this again goes to this indeterminate form, as we say, infinity over infinity. So now the problem becomes these powers of e to a negative x and negative 2x powers, right? So we could try something similar here, like we did in the last part, and try to multiply this function by some power of base e that helps us manipulate it so that we get something that is non-indeterminate. So let's rewrite the limit again. Limit x goes to negative infinity of 2e to the negative x plus e to the x over 3e to the negative 2x plus e to the x. So we think, well, what could we multiply here to get rid of one of those negative powers of e? Let's just try one. Let's try to get rid of the one in the numerator, e to the negative x. If I want to do that, I can multiply by e to the x over e to the x, right? E to the x never 0. And thus, we get the equivalent limit as x goes to negative infinity of, well, now notice in the numerator, 2e to the negative x times e to the x is just a 2. And then plus e to the x times e to the x is e to the 2x, all divided by 3e to the negative 2x times e to the x is a 3e to the negative x, and then plus another e to the 2x. So does this help us? Well, as x goes to negative infinity, e to the 2x goes to 0, top and bottom. And then notice that we're left with just that constant 2 in the numerator, and 3e to the negative x is going to become infinitely large still. So this goes to kind of, if you will, 2 over infinity. It's approaching that 2 divided by bigger, gigantically bigger and bigger and bigger numbers. And of course, when I divide a constant by gigantically larger and larger numbers, that's going to go to 0. And hence, limit as x goes to negative infinity of my function k of x here is equal to 0. Long run behavior. And to see the graph, here is the graph of this function. K of x, as we can see, as x goes to infinity, this function is approaching the output value of 1. And as x goes to negative infinity, the function is approaching the x-axis, otherwise known as y is equal to 0. And so, again, for these reasons, we can write that the lines y is equal to 1 and y is equal to 0 are both horizontal asymptotes of this function here, k of x. So I hope that gave you some examples, some ideas of how you can approach finding the long-run behavior of functions, particularly when they have some type of horizontal asymptotes. And so this video, right, we defined what a horizontal asymptote was, and we looked at a variety of examples. And now we can move on to other things. We're going to start focusing on the concept of continuity in the next video. So that's it. That wraps up the video. I hope it helped. And until next time, math and beats. Later.